My talk will be a prequel of Lena Noack's talks this morning, in the sense that I will go back a little bit to basics about habitability, exoplanets, and I hope you will find it simple. So the story is that, as you know, really back to basics, we've been discovering planets, exoplanets around other stars since 1995. Through different techniques that I won't detail, but the story is that through radial velocity, transit, using different kind of a system, in particular from space, and in particular with the Kepler Space Telescope, gravitational lenses, direct imaging, astrometry, lots of methods. I was happy to put this slide today because I checked the official number of exoplanets that has been detected and listed and confirmed. And today we have 3,999 planets, almost 4,000, maybe tomorrow 4,000. Discovered in, we have almost 3,000 planetary systems. So we're starting to have a lot of planets. You see this graph, I don't know if you see it very well, I don't know if you dim the light, no, it's okay like that. Or close the door. So you see the planet mass, a function of year of discovery, starting in 95, and you can see that it's only in the past 8 years that we're able to detect planets which are about the mass of the Earth. But we have discovered a lot of super Earths, I will say, things that may be terrestrial, rocky planet, and not mini Neptunes or Neptunes. So, what to get from that? Well, the first lesson, and I won't go back much to that, is that the solar system is not typical at all. That's the key point. We have discovered a lot of different kind of planets in every size. There is a kind of continuum. I won't detail. There are some interesting features in this mass distribution, but typically we have found super Earths, mini Neptunes, hot Jupiters, possibly ocean planets. You have planets around multiple star systems. You have lots of multiple star systems. You have very eccentric orbits. You have very compact system. You see the effect of planetary migration, which seems to have been limited. Maybe not, in the solar system. Well, this is the first lesson. The solar system is not typical. At least, for instance, having a Jupiter, a planet like Jupiter at this distance from a star like the Sun, it's quite exceptional. We will not be able to detect the Earth or Mars or whatever around the Sun-like planet. The second lesson is more interesting. It's a revolution that no one cares about, is that we have demonstrated in the past few years that nearly every star hosts at least one planet, more or less. And there are lots of planets, and no one cares in the sense that everyone knew that because everyone has seen Star Wars and Star Trek. And so there is no surprise when we say, oh, we have discovered that most of the stars are host planets. Okay, we knew that. No, this is new. We could have demonstrated the opposite. But that's a big revolution. Just like 95, the first planet was a revolution. This is based on statistical work, because everything is biased in the observation, is very important. So of course, when you know that, you want to know this question: what is the environment on other planets? Where are the planets suitable for life? Are there other Earths? All these stories, these questions that have been asked for thousands of years, and that's what we address today. So when you go there, you have to go, especially in such a school. We're talking about habitability, so we have to ask what is life and what's needed for life. Of course, I won't address that. That's my first point. But all these slides explain to you what maybe you will repeat. I've seen you purification say many times. As far as you understand, there is one thing which is useful. It's liquid water. So what we know is that life as we know it is based on carbon-based chemistry in liquid water. Carbon life without liquid water is, well, first point there, 95% of known chemical compounds are carbon-based. I'm wondering if this is coming from one of your slides. No? This is at least from one of your workshops. And so carbon without liquid water is really difficult to imagine and maybe difficult to recognize and detect. So on this basis, because when you talk to specialists of organic chemistry or whatever, and you ask them, can you imagine a life? It's really tough. We tend to do this hypothesis: habitability is equal to liquid water available. I'm sure you've seen that before. And this will be our hypothesis today. It's good because I'm a physicist, so the only thing I will care about is, can we have liquid water? So to get liquid water, back to basics again, it seems that water, H2O, is abundant. You need really a specific process to remove water from a given body, a planet or a moon. The problem is to get it liquid. So to get it liquid, you need an absolute pressure higher than typically 5.1 millibar, the triple point of water. And if you go too high in pressure, then even at normal temperature, where you will expect liquid water on the Earth, well, if the pressure is too high, then you have high pressure ice, we call it. So you go back to some ice, high pressure ice, even if it's warm, no more liquid. You need, of course, to be above freezing temperature, and you need to be below boiling temperature, which depend on the pressure. So it's in this blue region on this phase diagram. You all know that very well. And that's not always easy. So in the solar system, I'm sure you know where you find liquid water. You find liquid water on the Earth, and as mentioned this morning, and I think this morning and maybe yesterday, the other places where you find a lot of liquid water are not on terrestrial planets, but in the moon, mostly in the moon of the giant planets, Europa, Ganymede, Callisto, probably on Titan, Enceladus, possibly on Triton or on Neptune, possibly on Pluto, and even possibly on Eris, which is a Pluto-like planet among the trans-Neptunian objects. We believe that all these bodies may host a subsurface ocean. It's because they are mostly made of ice. The ice at the surface is very cold. And if you go deeper and deeper, at some point you reach the 0 degrees Celsius temperature. And if the pressure is not too high, then you can have a layer of liquid water. And this liquid water, altogether, it's much, much, much more than what we have on the Earth. So this is, of course, where you can consider all these words, at least the one where you expect to have liquid water, to be habitable. But in reality, they are not completely habitable. Well, they are habitable, but they are not as habitable as the Earth, because we have to define a kind of hierarchy in the habitability. The reason is that all these water environment, of course, are in the dark, with more or less chemical compounds, whereas on the Earth, of course, what is really important is the fact that the liquid water was on the surface, so it could benefit notably from the photosynthesis on the surface of the Earth. This is a lot of energy. This is a source of energy that has enabled the life on the Earth to change the environment, change the atmosphere in what we think is a detectable way from another solar system, stellar system far away. And this is a key point. So, the definition of habitability remains, I think it's a consensus that habitability means liquid water available, but it is also true that some habitable worlds are more habitable than others. First reason, as I just said, is the quality of habitability depends of if you have stellar light available, and the amount of different chemical species and energy resource that you can get to have life active. And secondly, something I didn't mention, but the duration of habitability will matter. If you have liquid water from a few seconds every millennium, it has no interest. But on the other hand, the Earth, if you look at the history, you all know that, has been have hosted liquid ocean for billions of years, and that has been a key. Within that context, various authors have suggested that we could define different kind of habitability, and sometimes it helps us to think. So class 1, first class, very good, are planets with permanent surface liquid water. That will be like the Earth. Class 2 will be, it's a little artificial, but it's a good way to think, planet which used to be class 1, but which has evolved. So the environment was very favorable for life to emerge as far as you understand it on the Earth. Maybe you have surface liquid water, that is good, access to solar energy, that is good. But then it evolves, no more liquid water, but then you can keep liquid water somewhere, typically in the subsurface, so that the life that has started, once it's evolved in Earth, is very, very robust and can evolve and live in the subsurface. That could be the case of Mars. It could also be, you can in some way put Venus, some authors put Venus in this class in the sense that we now have liquid water rich clouds in the upper atmosphere, in the mid-atmosphere of Venus, and maybe there you could, in theory, imagine some life to be happy there, to survive there. It's very, very speculative. Class 3 are bodies with subsurface liquid water, oceans, in interaction with the silicate mantle. These are the big star in the solar system, Europa and Enceladus. You really have active volcanoes, an ocean, and a crust of ice. The problem with these bodies is that there is no access to light, solar energy, and photosynthesis. Class 4 is bodies which they have a subsurface ocean covered by an ice layer, but at the bottom you have another high-pressure ice layer. So you can imagine these oceans to be very chemically poor. There is no light, of course. Recently, this has been questioned. It seems that even on body like Ganymede, where you have this liquid water sandwich between two ice layers, you have volcanic activities at the bottom that create convection in the high-pressure ice layer, the one which is there, that is able to move some chemical compounds from the silicate mantle to the ocean. So maybe Class 3 and Class 4 could be put together. This is these are recent development. So as I told you, the problem in these two bodies is that there is no access to light, and also when you are outside them, even from the Earth, when we look at Europa and Enceladus, and it's even worse when you look at such a body around another star, is that it's very difficult to investigate if there is life there. So they are a little less interesting. On the opposite, Class 1 planets are the ones which are of interest because you can have surface liquid water. It allows photosynthetic life. It can modify its environment. It probably helps to have more complex life. But the key point is that these are the kind of bodies on which we can detect remotely with telescope living activity. So on this basis, most astrophysical studies, astronomical study, I should say, focus on these Class 1 planets. So we are going to continue and forget about Europa, Enceladus, and similar bodies. On this basis, it has been defined the infamous habitable zone, which really is the key, the tool that we use to understand and try to speculate if this or this planet will be habitable, in the sense Class 1 habitable, with liquid water possible on the surface of planets. I said it's famous because it's criticized a lot. If you can look at the literature, there are lots of misunderstanding. The typical, when I give such a talk without being careful, right away someone raises its hand and says, how about Europa? It's not in the habitable zone, but it's okay. We all know that. The origin of this problem is because the habitable zone has two origins. Originally, the habitable zone was just defined to represent the conditions that Earth enjoys. At a time when the existence of liquid water in Europa, on Enceladus, was not well known. So if you look at the literature in the 60s, 70s, even later, it's all about liquid water on the surface, oceans, that's it. Now we still use it, not because we are Earth-centered, but because we are interested in life on the surface so that we can detect it. So habitable zone concept is now designed to prepare observation for astronomers looking for detectable life with ideally photosynthesis. So that's why the name is not very good. Frank Sersis suggested to call, instead of calling the habitable zone HZ, it's often called HZ, to call it the hunting zone. It's a little clear. No, I know we prefer the surf zone or something like that to really demonstrate that it's surface liquid water. So the key point is that it's surface liquid water because this is where we can hope to detect life remotely. So, to go more in the details, because again, in many meetings I go, this is debated and so on, it's important to understand that there is only one habitable zone per star. What I mean is that around a given star, the habitable zone is the region where you can have on a planet surface liquid water, meaning that it's the region outside which it is not possible to have a rocky planet maintaining liquid water on its surface. So outside the habitable zone, no water is possible. So inside, it doesn't, of course, being in the habitable zone does not mean that a planet is habitable. For instance, the moon, our moon is in the habitable zone, but of course it's not habitable. There's no atmosphere, no water, no liquid water, so no problem. So the key point is that the habitable zone does not depend on the planet. You cannot say the moon is not in the habitable zone because it has no atmosphere. The moon is in the habitable zone. It has no atmosphere. So as a consequence, it is not habitable at all, given all these definitions. Okay? Of course, I will show you that depending on the definition you gave to the habitable zone, you could still define different kind of habitable zone, but it does not depend on the planet. More later. So the next step in this story is that we want to characterize the habitable zone. In particular, define the limit. The reason why we call it a zone, of course, is because if you're talking about surface liquid water, you are on a planet. If you're too close to the star, at some point the temperature will be too high. It's not possible to have liquid water. Everything will be in a vapor state. If you're too far, it's too cold, all the water will be frozen. So you can demonstrate, and it's been felt for many years, that this is a range of orbit, the habitable zone, that can define the habitable zone. So the question now is, what are the boundaries? How extended is the habitable zone? It's a problem of climate of an atmosphere. It's good because I'm a climatologist, so I can study this. So now I will open a little side story about how we study climate and atmosphere on other planets, and in particular the kind of tools. If you're interested in this literature, you have different models that have been used to do that. When you work on that, you can demonstrate that the key parameters controlling the climate on terrestrial planets it's not an infinite list. You really have three big hypotheses. The first is the stellar insolation. Typically, you have to know the orbit and the kind of spectra, the star spectra that force the climate. That's a good thing because this is the kind of thing when we observe a specific exoplanet, we know about the star, we know about the orbit. The second point, the third, I will go to the third directly, you have the rotation. The rotation controls many things. It controls the distribution of insolation, installation, some people say, and also it controls the atmospheric dynamics. Depending on the rotation, the redistribution of heat will vary. That's why rotation is very important. And of course, the big problem, I'll go back to that, is the atmospheric composition and the surface volatile inventory, the amount of water you have. That's a big question. But when you know these three parameters, you can more or less estimate the kind of climate you have, and then estimate if the planet could be habitable. And to do that, of course, you will use climate modeling. This is what we and many other teams are doing in this field of studying the habitability. So you have different kind of models that has been used to do that, and different kind of models are still used in the literature. So if you're interested, I will give you a little more details. The first kind of models are what we call the 1D global radiative convective models. These are the ones that have been used to really define the habitable zone in most of the studies you will see. And the most famous paper are the paper by Jim Casting, especially his masterpiece in '93 called Habitable Zone around the main sequence star, and the following papers by his student and colleague Koparapu, that's still publishing a lot with this kind of models. How this kind of model works? Well, the idea, if you're not familiar with that, is that you take one column of atmosphere and you assume that this will represent the entire planet. So you take one column of atmosphere, you put some gas there, and you put some insolation. Not an insolation, you estimate the mean insolation at the top of the atmosphere. You can demonstrate that the mean incident angle of the sun will be 60 degrees. So every 1D model always take 60 degrees as an incident angle. And the mean incident flux is actually what we call the solar constant, stellar constant, the amount of heat, amount of radiation in watt per square meter which is received where the planet is, divided by 4. Divided by 4 because the surface of the planet is 4p radius to the square, but the cross section is p radius to the square, so it's divided by 4. It's very, very standard. So you take this, you put the equation, you write the insolation. You have to assume a surface albedo, the amount of radiation which is reflected back to the atmosphere. You have to compute the radiative transfer to estimate how much photons are reflected or scattered by the atmosphere. You have to do the same in the thermal infrared. You have surface emission, you have absorption and emission in the atmosphere. This is where you will account for the possible greenhouse effect of your atmosphere. If you have gases that can absorb the thermal infrared radiation, they will create a greenhouse effect. And this is why it is called convective models. If the temperature profile is unstable, if you have warm air below cold air, you have convection, vertical mixing, so that you go to what is called a neutral profile, which is defined typically on the Earth. It will be about 6K per kilometer. So how to compute the radiative profile from these relative convective calculations? I'm going into details because this is very important in the literature. The first way you can do is what we call a time marching model. You start from arbitrary initial state. You say, I start with my planet is 0 degrees Celsius. I have this gas. It's all isothermal, and I let it go. And then you let the model converge to equilibrium to know what's going on. You can play with the model that we have put online in our lab. It's made by Martin Turbet. This site, you've seen the address. It's a website where you have online a 1D relative convective model with which you can play to explore the kind of climate you can get. But in practice, most paper has been done using another trick which is called inverse climate modeling. It's very simple. This is the story. You take this typical 1D atmosphere. This is altitude and temperature. And you assume that the temperature profile is always defined by an isothermal stratosphere. You can demonstrate it's realistic more or less with typically 200 K. And below a given level, you have a troposphere with what we call adiabatic lapse rate. It's the lapse rate of water of atmosphere which is stable. And then you do the calculation to see the kind of surface temperature you get for a given atmosphere, a given star, and so on. It's designed to compute the solar flux needed to achieve a given surface temperature. That's why it's called inverse climate modeling. You say, I want this temperature, at what distance do I have to be from a given star? This is the way it's done. So in practice, here is what you do. You set the surface temperature. So immediately that defines, based on the assumption I just told you, a temperature profile. Once you have the temperature profile assumed, you can estimate the amount of water vapor which will be in this system, because the amount of water in the atmosphere will depend on the temperature profile. Typically, you can assume you are 80% saturated, for instance. That's a typical thing. When you have done that, it's quite simple. You do the radiative transfer to compute what happened to the photons coming from the star, and you can estimate the mean planetary albedo. And you do the calculation to estimate, since you know the temperature, the thermal infrared, the radiation transfer. And typically you estimate the amount for this given temperature, the amount of radiation that is radiated by the planet. That is called the outgoing thermal long wave radiation. And once you know that, because you have an equality between the amount of radiation from the star which is absorbed by the planet and the amount of thermo-infrared radiation that is radiated away from the planet, you can directly estimate the flux of stellar radiation you need for this surface temperature. So it's weird, but each time, for many of the papers about habitability, you will see what is done is say, for instance, we need 0 degrees Celsius. How far can we are we from the planet, from the star? It's not the opposite, and it takes some time to get familiar with this way of thinking, but that's the way it's done most of the time. So these are the old traditional studies papers since the 70s, 80s maybe. But now, of course, we can use more sophisticated models. You can use, there have been some papers with the 2D energy balance model. You have lots of work which are done with what we call theoretical 3D general circulation model. The goal being not to really study the exact climate, but to study the atmospheric circulation typically. And finally, what is really new in the past 5-10 years are the use of full global climate models, which are much more realistic, much more ambitious, which are in practice aiming at building virtual planets. In other words, aiming at simulating everything that is going on the planet, not at all something simple, something complex with all the details, the clouds, the dust, the ocean possibly, and so on. So how can you do that? Of course, it's much more complex. When you see this movie showing the circulation on the cloud on the Earth, you tend to think, wow, this is too complex. You have an infinite amount of degrees of liberty. You have a different scale which are coupled. It looks very complex. In reality, for instance, this movie is not coming from satellite observations. It's actually coming from a model. And in fact, for the Earth and for the other planets, we have now a good confidence of our ability to simulate to first order the climate on the planet. And the reason is that even such a climate system is defined by a limited number of differential equations. And once you learn how to solve them, you can simulate the climate. Of course, in the details, it's difficult. As we discussed earlier today, knowing exactly what will happen to the Earth in 50 years, it's a complex problem. But it's a problem when you want to know the details. You want to know if it's going to rain in China or not, or if the temperature will increase by 3 or 4 degrees. But the model is able to very well, any model, even simple, is able to do very well to simulate the climate on the Earth. So in practice, you have to solve the differential equation. This time I will go fast. The first thing that you have to do, which is new compared to 1D relative convective model, is to solve the large-scale atmospheric motion, atmospheric dynamic equations, the fluid dynamic equation around the rotating stars. I won't show them. And to force this fluid dynamic equation, at every grid point, you have to solve the detail of the climate, almost as if it was a 1D relative convective models. You have to resolve the relative transfer at stellar wavelength and in the thermo-infrared. You have to compute the thermodynamics of the surface, the details of what we call subgrid scale dynamics, the mixing by the atmosphere, the turbulence, the convection, and something which is always very difficult is to understand the volatile condensation in the surface in the atmosphere. In other words, the cloud macrophysics, the formation of snow and ice, the hydrology. That's really complex. But you can do things and more or less simulate the climate. When you do it, you quickly realize that all these different equations can be solved independently. And when you put together different bricks that solve the different process at work, it's like using a game of Lego of bricks. You put the bricks together and you can simulate a planet, the Earth, Mars, Venus, an exoplanet that you can imagine. It's really a tool which is now, with the experience we have, is usable to study any kind of climate around any star. In the solar system, we have tested them on all the atmosphere that we have. We have 10 atmospheres in the solar system. Do you know them? It's a quiz. Of course, you have Earth, Venus, and Mars. You have 6 terrestrial atmospheres. So after that, you have Titan around Saturn. You have Triton around Neptune, it's a thin nitrogen atmosphere with hazes and clouds and geysers, lots of things are going on. And Pluto, the dwarf planet with a beautiful atmosphere of nitrogen with the hazes and lots of activity. And of course, we have 4 giant planet atmospheres, so that's 10 bodies that we can study and on which we have been able to test our ambitious global climate model, so that we have been able to learn many things. For instance, I put again the 6 terrestrial atmosphere on which we have tested our global climate model. I say we, it's our team in Paris, but many other teams around the world. We have also been able to test them to do paleoclimates. This was discussed earlier today, but even for ancient planet. So you can see here, I show that with the amount of observation available to constrain the GCM. So it's interesting, for instance, even if we don't have direct access to the meteorological data from past Earth, we can test our global climate model on past Earth because we have records, geological records to do that. It's the same for Mars, for even Pluto, and so on. And on this basis, we have gained enough confidence to simulate planets that we don't know at all how they are, but we can explore the kind of climate that are possible and then explore the habitability. So back to my, my story about the habitable zone. The first question I will ask is, what is the limit of this habitable zone? In other words, where is the inner edge of the habitable zone around a given star? So to define that, let's take the Sun, for instance. You can just ask the question, if I take a planet like the Earth, or with oceans on it, how close can I get to the Sun-like star and remain habitable? Special effect. And what is very interesting when you do that, I'm sure many of you knows this problem, is that you get unstable very quickly. Very quickly, if you move the Earth toward the Sun, the Earth becomes not habitable. The reason is the following. If you increase a little bit the solar flux, you increase the temperature at the surface, you increase the evaporation of the ocean, because you assume you have an ocean, you increase the greenhouse effect, that increases the temperature. This is a very strong positive feedback, and you really change the climate very quickly when you do that. The historical Sorry?
You change the albedo with the clouds, no?
A little bit. I'll mention that. Historically, the first studies, the reference studies, have been done in 1D in which clouds have been neglected. So this is the real, the typical reference for the 1D results. You have early finding of this. It's called this process is called the runaway greenhouse effect. I'm sure you have heard about it. Here is how it looks. This is a paper. This is a plot from Koparapu et al. 2013, but it's really like all the other papers I mentioned here. It's obtained by a reversed climate model, so you have to read it carefully. The axis is surface temperature, and the y-axis is relative solar luminosity. What it shows is that if you start at the solar luminosity of 1 being what we get on the Earth today, temperature is around 300 K. If you increase just a little bit, very quickly the temperature increase. I should use this. Temperature increase. And if you continue increasing it by a few percent, just as if you were moving the Earth by a few percent, quickly you completely vaporize the ocean on the planet. You put all the water vapor in the atmosphere. The water vapor is a strong greenhouse effect. You block the infrared radiation so that the only way for the radiation to get out and be in equilibrium is for the surface temperature to go beyond 2000 K. So it's a completely different planet. You're not habitable anymore. In this plot, you can see that you do that if you move the Earth by 3% toward the Sun. You vaporize the ocean right away. This was and still is the reference with 1D model. Of course, it has been interesting to study it with 3D models. Because, for instance, we could speculate that if you increase the amount of water vapor in the system, you will increase the amount of clouds. Maybe the clouds will raise the albedo, protect the planet from this extra heat, and maybe the Runaway greenhouse effect will happen much closer to the star. So this has been done by in various studies, in particular with Jérémy Lecomte, a scientist who's now in Bordeaux, using our model. We've done this. It's a complex problem because you have to simulate what happened in an atmosphere. We have suddenly a lot of water vapor in the system, so it's not a well-mixed atmosphere with only nitrogen. For instance, if you study the Earth, you have water vapor, which becomes a major component of the atmosphere. It's difficult to model, but it's fun. And what we find, we were expecting that the clouds maybe could protect and increase the albedo. That's not what we found. We found that the clouds tend to form high in the atmosphere and actually increase the greenhouse effect. Because when you have high clouds, they are cold and they increase the greenhouse effect. So they actually tend to warm the surface. However, we find that compared to 1D model, the dynamics is such that you have lots of area where water vapor is unsaturated. In other words, even if you have a lot of water vapor in the system, you have area which remains dry, and so that the radiation can escape. This is how it looks. It's a little complex, but this shows the humidity. In red is when you have low humidity, and in the tropics, for the same reason that you have low humidity in the Saharan desert, for instance, you still can radiate thermal radiation, and you can cool the planet and prevent a little bit the runaway greenhouse effect. But at the same time, the clouds tend to increase it. So in the end, we find not much difference. In a 1D model, you will have the runaway greenhouse effect moving at 0.97 astronomical units, moving the Earth by 3%. In 3D, you could just prevent it until 0.95. So it was interesting investigation to do it in 3D, but the results are not super striking. Another thing that was found with 1D model is that even before, in some models, most models, even before you actually have the full vaporization of the ocean, you tend to actually lose your ocean to space. The reason is the following. When you increase the radiation by moving the planet toward the star, you increase the surface temperature, as we said, and you will allow water vapor to escape. Let me explain to you. On Earth nowadays, you have a wet atmosphere, but water vapor cannot go very high because the top of the troposphere, around 10 kilometers, is so cold. You know, when you take a plane, it's minus 50, minus 60. You have no more water vapor. All the water vapor has fallen down as ice crystal. So here it's super dry. As a result, the sun UV radiation cannot really photolyze water vapor there because there is no water vapor. If you increase the surface temperature, you move this cold trap up, seriously, so that the UV radiation can actually photolyze the water vapor. So you have OH and H, and once you have hydrogen atoms that are free, they escape, they're so light, they escape very easily. And when you do the calculation, you find that if you are in such a state, you can lose the ocean on the Earth in a few million years. This is a plot showing what is called the water loss limit by casting. This is the solar luminosity and the surface temperature again. I showed you this plot before. When you hear moving the Earth by only 1% in this model, you can see that the amount of water vapor in the atmosphere in this model will increase a lot. This is the profile of water vapor. It's a log scale model. I don't know if you can see here. This is what we have on present-day Earth. You have 10 to the minus 2 mixing ratio in the atmosphere, in the troposphere, and almost nothing in the above 10 kilometers. But if you increase a little bit the surface temperature, for instance, up to 320 K and 340 K, you can see that the amount of water in the system is much, much higher. That's what is called the wet greenhouse effect. And so that even you can completely wet, can I say that? The upper atmosphere by just increasing a little bit the surface temperature, according to this model. And according to this model, you will lose the ocean of the Earth relatively quickly if you move the Earth by 1%. Recently, we've done a little more sophisticated modeling, and we found that it's not so obvious because the assumption about this isothermal stratosphere, I'm sorry to go into the details, but I'm giving you all the details of the current debate in the community. We find that if you do the iterative transfer of the upper atmosphere temperature, instead of having exactly 200 K, when you put water vapor, you tend to cool it and you prevent the process. That's what we found. That's what we published in Nature with Jeremy also. And this will prevent the story about the water loss limit. But this has been questioned by other papers. So there is an active debate currently whether or not, if you move the Earth by 1%, you lose the ocean or not, or if you go directly to runaway greenhouse effect by moving it by 5%. These are in some way details. The problem is that you understand, right now, the Earth, of any planet that will have ocean on its surface, is very close to this runaway greenhouse effect state, and the Earth is very close to the edge of the habitable zone. It is impossible for an Earth-like planet around a Sun-like star to be closer to the big, closer to the Sun and have liquid water ocean. Of course, you can find some detail that suggests that it can be otherwise. For instance, it has been shown that if you, instead of having an ocean planet or a partial ocean planet like we have on the Earth, you have something much drier. Many authors call that a dune-like planet from the famous science fiction novel Dune. If you have not much water on the system, water will tend to accumulate in the polar regions where it's cold. This region will be super dry, and you can demonstrate that with such a planet you can move closer to the Sun without going into runaway greenhouse. And you can even demonstrate, that's been done in various papers, that this runaway greenhouse limit will depend on the mean insolation at the edge of the polar cap, the polar sea. And it is mentioned that then the runaway limit is significantly extended, but not you cannot move very close to the Sun with this process. Let's now go to the other side of the habitable zone. What is the limit of the habitability for Earth-like planet, for instance? How far can you go before completely freezing a planet from the Sun? Interestingly, if you do that with the Earth, not easy, but in a model you can do it, you find that the limit is also very close. And the reason is the following. If you move the Earth further away from the Sun, you have more ice and snow, the albedo increase. If the albedo increase, you reflect more radiation. If you reflect more radiation, you lower the temperature again. So this is another positive feedback. Your world solar flux, temperature is lower, more ice and snow, the albedo increase, and you enhance this cooling. When you do that, I don't know if I have a slide for that. When you do that with the model, you find that depending on the model, by moving the Earth by a few percent, you go into what is called Snowball Earth state with the present day atmosphere. I will illustrate that to you with a little movie we've done when we studied the early Earth. It's a climate model I will show you. You move the Earth by 12%, so you will receive 79% of the insolation. This is a plot mapping showing the albedo, so it's the color scale is such that white is like snow, more than 40%, and blue, more or less, is lower than 3.3. We start at year 0. This is at spring equinox, and we'll see what happened. We just took the Earth and moved it by a few percent. Oops. When you do that with the Earth climate model, you get this. Very quickly, you have lots of snow on the continents, and the snow survives during summer. So you enhance the albedo. It's the temperature cool, you get sea ice, and the sea ice tends to really cover the mid-latitudes. You lower the anti-albedo, the planet continues to cool, the sea ice goes to the tropics, and finally, after only a few years, finally the Earth will be completely frozen. And after about 25, 30 years, you have no more liquid water, it's all very cold, and just by moving the Earth a little bit. You get this kind of temperature after 30 years. These are the annual mean surface temperature. It's about minus 55 in Bordeaux, so it's not good for the wine. And it's not good, it's a completely different planet. What is fun also, you may know that, if you take this Earth and put in such a model and put it back where it is, it remains cold because the albedo is so high that it's locked into this snowball state. So of course, it's not that simple. This is assuming the present-day Earth. In reality, the Earth has been the insolation on the Earth when billion of years ago the Sun was weaker, and 3 billion years ago actually the insolation was like that. Yet we all know that the Earth was covered with an ocean. It's called the faint unsung paradox, and it was not like that. The Earth was warm, actually relatively warm. There was probably no ice cap, and the reason, of course, is because the atmosphere was not like it is today. You had more greenhouse effect. And indeed, if you take the same model, as I told you, if you have the present Earth atmosphere, you're super cold. But just by multiplying the amount of CO2 by 2.5, you can prevent, thanks to the greenhouse effect of clouds, it's a little tricky, you can prevent the global glaciation. And if you increase the amount of CO2 by 250 and you put some methane, this is again related to the kind of studies we do to understand the past climate of the Earth, you can prevent the freezing and have a relatively temperate planet. So in reality, the habitable zone, I told you, is wherever you can hope to have a planet with surface liquid water. The real question is to know how far can greenhouse effect keep a planet warm enough to have liquid water on its surface. So it's not like only the Earth, like present-day Earth fate, but you have to understand how far can we have, assuming greenhouse effect, a liquid water on the surface. So what you find is that it's not an infinite limit. You cannot add greenhouse gas and go very far. Typically, if you take a standard greenhouse gas like CO2, even if you had methane or whatever, you cannot go beyond a few tens of %. Here is the plot to illustrate that. This is the minimum flux to get mean surface temperature at 0 degrees Celsius, in other words, to remain habitable. And this is the amount of CO2 that is needed to remain habitable. So what you can see is that, you can read it that way, if you increase the amount of CO2, you can get away from the sun. You can have a flux which is half or 1/3 of what it is today. But if you continue to add CO2, it's useless. The reason is that the more you add CO2, of course, the greenhouse effect of CO2 will increase. But because CO2 is also a gas that will scatter the radiation, it will increase through Rayleigh scattering the albedo of the planet, so that if you add too much, it doesn't help, because the main effect which will dominate is the fact that the planet will become brighter and brighter because of the gas that you add, without increasing much the CO2 greenhouse. So you can demonstrate that you can go up all the way to 1.7 astronomical units, and beyond that, whatever you do, if you add CO2 or even methane, it won't help. The only way to keep an atmosphere, well, there are several ways, but one way to keep liquid water ocean on the planet while being further away from this limit is maybe by taking into account clouds. We could demonstrate some time ago that in a cold atmosphere with lots of CO2, I use CO2 because this is really common. It's what we have on Venus, on Mars, we used to have on the Earth, it's what we expect to have on many planets. If you have a cold CO2 atmosphere, you tend to form CO2 ice clouds. These CO2 ice clouds to the eye look the same than water ice clouds, but in the thermo-infrared, they can do something that water ice cloud cannot do. They can scatter the infrared radiation. And this creates a very strong greenhouse effect called the scattering greenhouse effect, and can actually increase the distance from which you can remain hot, warm, around a sun-like star. But this is a little speculated, and in fact we did some 3D modeling of this and it doesn't work very well anymore. I won't detail that. Finally, there is one special case that has been put forward recently, is the case of hydrogen-rich atmosphere. So far I've talked about planets which are atmosphere, which are Earth-like, or what we can imagine for a terrestrial planet. CO2, methane, nitrogen, water, stuff like that. But if you assume that on a terrestrial planet you can have a thick hydrogen atmosphere as if it was a Neptune, if you want, or not too much, but then you can have a relatively warm climate. The reason is that at relatively high pressure, if you have like a few bars of hydrogen, then hydrogen can become a good greenhouse gas thanks to a process called collision-induced absorption. I won't detail that. One molecule of hydrogen is not a good greenhouse gas, but when you put high pressure hydrogen, it absorbs thermoinfrared radiation. We believe that either you are like a Neptune with millions of bars of hydrogen, so no surface, or you're like the Earth, and then you tend to all the hydrogen escape. It's an open question. You also can demonstrate that if you start with the primordial hydrogen atmosphere and you escape it slowly, at some point you will have the exact amount that enable the surface to have liquid water. And this will last for millions of years, or hundreds of millions of years, depending on the escape model. Okay, I won't detail that too much. What I just want to illustrate before moving on is that all this story started by a first paper in 1999 by Stevenson. It's a very short paper. This is the entire paper, speculative. But what he said is that if I assume hydrogen atmosphere, I can have a greenhouse effect that is so strong with a thick hydrogen atmosphere that just the geothermal heat will be able to keep the ocean liquid on the surface, so that you have planets in interstellar space far from any star and still have liquid water on the surface if you have a good enough hydrogen atmosphere above it. So it's interesting speculation, and that's already 20 years ago. So in summary, this is what we have around a sun-like star. This is the habitable zone. The likely habitable zone will be 95 AU. The limit, if you go beyond, closer to that, you need to speculate about, and I will go back to that, the fact that you don't have too much water and the water is stored in the cold regions, or you have clouds protecting the system and so on. And beyond, below 0.5 AU, it's almost impossible to have liquid water on the surface. On the opposite, if you're around there, you need some greenhouse gas, and beyond 1.5 AU, 1.7 AU, you have to assume something special, either a special greenhouse effect by clouds or some help from hydrogen. Now, this is for the sun today, a sun-like star, and without at this time. Of course, habitability can evolve through time. And time, of course, is very important. So that's a very standard plot, but time is necessary for life to arise and evolve. I'm repeating things that you already know, but of course, the Earth formed 4.5 billion years ago. We don't know when life started. It was discussed this morning, maybe if some clues about 4.2. I understand you were not super convinced. But we don't know. Here I put a date for multicellular life, also it's speculative, but you can see, even if you take this very typical number, it took 2 billion of years to start multicellular life. And the first animals, I mean the one that we are coming from, are maybe 5-6 hundred of million years ago. And then it took a lot of time to get to intelligence. You may ask me, are we intelligent? I'm not sure, but there is a definition used not by us, but by, for instance, people who are interested in extraterrestrial intelligence communication. The definition will be if you are able to build radio telescope. So we are intelligent because we can build radio telescope and communicate and try to communicate with other intelligence. So it takes a lot of time. The problem is that habitability is not constant. Things evolve. The first things that evolve are the stars. I mentioned it already, but a star flux evolves so that the habitable zone evolves. This is a typical plot you can get on Wikipedia. This is the evolution of the sun. The reason, as most of you know, I'm sure, is that the sun is a thermonuclear reactor. You take hydrogen and you have fusion and then you get helium. With time you get less hydrogen in the core and more helium. The density increases so that the amount of heat released by the sun increases. In practice, it's not really the temperature or the how do you call it? Brightness temperature of the sun that increase. It's really the size. The size of the sun increase in size so that even if its temperature doesn't change much, you have more and more radiation. You can see the luminosity here. As I mentioned before, when the sun was young, it was maybe 25% weaker than today. Through its main sequence, its radiation has increased, its flux has increased, and it will continue to increase. This is today, of course, and it will continue to increase in the future. As a consequence, the habitable zone that I defined earlier is moving. This is a plot showing you the solar system habitable zones through time. This is the probable habitable zone, the likely habitable zone, and the maximum possible extension that I mentioned before. So I will use this plot to tell a few stories about the solar system, the lessons from the solar system. Let's start with the Earth. You can see that the Earth is here now. It started in the habitable zone, but far from the inner side limit, meaning that it needed some greenhouse effect to be habitable. And the greenhouse effect adapted until now. We have a weak greenhouse effect, believe me. And in the future, of course, it will leave the habitable zone in typically 1 billion years from now. It will be, in theory, the ocean will vaporize and will be the end of the world. So 1 billion years from now, we have time. What's interesting here is this, the fact that we had to start with greenhouse effect and adapt it with time. How is that possible? It has been demonstrated that most likely there is a process on the Earth that has adapted the greenhouse effect, the amount of greenhouse gas, so that the Earth could stay habitable all the time. This is very, very classical in this literature. The story is the following. It's called the carbonate silicate cycle. Everyone knows that? Have you discussed it before? So very quickly, what happened is that on the Earth, typically nowadays and in the past, you have CO2 in the atmosphere. CO2 tends to be, you have a sink of CO2 at the surface of continents through, typically the CO2 tends to dissolve in the liquid water, the fresh water. You have weathering on the surface. The fresh water will carry the CO2 and also take some ions from the silicate surface, like calcium. Everything goes into the ocean. You have accumulation of these ions, calcium for instance, and the CO2 dissolve, which is HCO3 minus. When you have this concentration is high enough, nowadays it's done by biology, but without biology, if you always can get to a high concentration, you make carbonates, CO3, and these carbonates accumulate on the floor of the oceans. And if you wait enough on a planet like the Earth, because you have plate tectonics, the carbonates will go into will be subducted into at lower level, where we have high temperature, high pressure metamorphism, and this carbonate will be released as you will have the reverse equation. CO2 will be released by the volcano, and you will have a cycle in which the CO2 taken here will go back to the atmosphere here. This cycle is a thermostat, because if you have a lower temperature, you have less water cycle, less rivers, less rain, so you have less weathering, And since CO2 continues to accumulate, you will have more CO2 in the atmosphere, you will increase the greenhouse effect, and temperature will be stabilized. It works very well. It is considered that this has enabled the planet to adapt to the evolving sun, and even to adapt to events that sometime to some period during which, for various reasons, the planet has been frozen. It's called the snowball state. You have complete glaciation. When you have complete glaciation, speculated, it's debated a lot, but when you have complete glaciation, you accumulate CO2 until you stop the glaciation and go back to a warmer climate. This is for the Earth. The question is whether plate tectonic will be likely on other terrestrial planets. Is it necessary to remain habitable for billions of years? No one knows. This was, of course, discussed this morning. I won't go back too much. It is not in the solar system, as discussed this morning by Lena. There is only one example of plate tectonic, and we have no idea if it's completely exceptional or not. We have no idea. We have models that shows that you have a regime where you should have plate tectonic or not, but they are a little biased by the fact that we have very experienced, we know very well the Earth case. I won't detail that, time is flying. The question is whether you have plate tectonic on small planets, on larger planets. This was discussed this morning. There is an interesting debate. You may remember Lena's diagram this morning showing that there is a lot of paper disagreeing about whether on larger planets, on super Earth, you can have plate tectonic. It's completely open. There is a question which is the Earth just right for plate tectonics? In the term of size, but Venus is almost the same size. There is no plate tectonic. There is a wall surface temperature, role of water in the mantle. You have to check Lena's talk again if you want to know these details. I went back one slide because the slide that I skipped just before stopping, someone came to me and asked the question related to this slide. So the question was, but if we don't have the plate tectonics to do this geophysical thermostat, then it doesn't work and we're all dead. And the answer is it's a strong idea that is in the community. If you talk to many of my colleagues working on these habitability problems and so on, many believe that the definition of the habitable zone is related to the existence of this carbonate silicate cycle that adapt the greenhouse effect to the distance from the star, to be sure that wherever you are in the habitable zone, you have the right greenhouse effect. But in reality, you have to be careful. And this is the plot I skipped, is that if you don't have carbonate silicate cycle, then it can work just if you have enough volatile. If you have a thick atmosphere, it's okay. For instance, it seems that it is possible that many exoplanets may be volatile rich. We have this idea because you see that we see many planets more massive than the Earth. So if you do the ratio between what was delivered to the surface and so on, you have thick atmosphere. You also see that in many cases it seems that planet has actually migrated a lot. So many may come from far away, beyond the snow line. In other words, be very volatile rich and move to the habitable zone. So in that case, it is possible. We don't know. But in a typical case is a Earth-like planet with a thick atmosphere. I don't know, 200 bars of CO2 or 50 bars or 10 bars of CO2. The point is that if you start the Earth with 10 bars of CO2 and you keep 10 bars of CO2, it's not easy, then it will be habitable from the beginning until now without problem. It will be quite warm at the beginning, it will cool a little bit, but it will remain habitable. You don't absolutely need the carbonate silicate cycle, and this is not what you will read in many review on this subject. I don't know if you got my point, but that was the question. So, or you can even, it's one way, for instance, to address one issue that was raised this morning by Lena indirectly, is if plate tectonics started 2 billion years ago, that's I think a very extreme number, how could we survive before? Maybe we had just 2 bars of CO2 and it was good enough. We had warm and we continue with 2 bars of CO2, and this thermostat, geophysical thermostat, only started later and enabled the Earth to survive later glaciation and so on. Okay? These are details. Okay, I'm going back to this plot. And now I talk about the Earth. Let's mention Venus. Venus, of course, now is well beyond the, outside the probable, the likely habitable zone. And indeed, it's not habitable. As you know, Venus is a very hot planet. The surface, you have typically 750 K surface temperature. Why? Because you have a very thick CO2 atmosphere, 90 bars of CO2, extreme greenhouse gas, almost no water in the system. This is typically the early atmosphere volatile, the present day atmosphere volatile inventory. You have 90 bars of CO2 in the atmosphere, almost no water, a bit of nitrogen. However, that we have all reason to think that Venus, the Earth, started with the same kind of inventory, typically 90 bar, 160 bars of CO2, lot of water, and some nitrogen. So something was such that the Earth and Venus did not evolve the same. The Earth, of course, most of the CO2 is now, as I mentioned, not in the atmosphere, but in the soil as carbonate. Some nitrogen must be there as well. And you still have lots of water on the surface. Venus evolved differently. All the CO2 is in the atmosphere and all the water vapor was lost. What happened? Our understanding is that it probably happened what you can imagine based on the story I've told you so far. A typical scenario is to say maybe actually Venus started wet. When it was there, it was not too far from the the inner limit of the habitable zone. And for some reason that I won't detail here, you could imagine that they started with an ocean. It's something that works. You take Venus, you put an ocean right now. With a faint sun, you can have an ocean that does not vaporize right away. So maybe early Venus was habitable. But the sun got brighter, and you had the runaway greenhouse effect. Either the full one or the wet one. In other words, either you really vaporize the ocean or you lost water vapor to space, but you lost the entire amount of water into space. This is what is observed. And when you had no more water cycle, a typical, you have no more water cycle, so no more way to keep the carbonate in the subsurface. So the CO2 accumulated in the atmosphere, and this is the present day Venus, no more water vapor, 90 bars of CO2, a very hot surface. That's a very standard scenario that you read it in many reviews. It's an exciting scenario because it suggests that for some time, maybe 1 billion years, you had an ocean on Venus, maybe life, dolphins, whatever. Of course, maybe more likely alternative scenario, more likely but not as fun, is that we never had ocean on Venus. The reason being that when Venus formed, like on the Earth, you started with the magma ocean, with all the volatile in vapor state around the planet. On the Earth, it cooled enough so that water condensed and formed the oceans. Maybe on Venus, because it was beyond or too close to the sun, below the inner, the limit, the runaway greenhouse effect limit, the water never condensed. You can demonstrate it works. You have lots of paper as I mentioned here. You can especially read this paper by Amano et al. In 2013 in Science. Water never condensed and in fact escaped right away without forming oceans. Right on Venus right now you have a very high day-to-age ratio, maybe by 100. The meaning of that, I'm sure you're all familiar with that, the idea is that it demonstrates that whatever water was there initially, it escaped. So it's a good story to say we started with a full ocean, everything escaped, and as in this scenario here, that's why you have this 100 time enhancement in the day-to-age ratio. But you can find other scenario. I will give you one example. Imagine you start with Venus with no more water at all, no more HDO, no more H2O. Then if you have one comet coming from time to time, this is about the amount that you have in the atmosphere. You have comets coming from time to time with their own D2H ratio, which is not so different from the one that you have on the Earth. The water puts water, HDO and H2O in the atmosphere. This water vapor escape, and it's enough, escape sufficiently to create this D2H enhancement by 100. What we will love is to be able to get to geological records, a little bit like we have on the Earth and like we have on Mars, to see how was Venus 3 or 4 billion years ago. Of course, we cannot, because when you look at the surface, you see many craters, and when you count the craters, you can demonstrate that the Venus surface was completely resurfaced by a global event sometime 1 billion years ago, roughly. So we have no access to what happened before. If you look carefully in the literature, you can find paper speculating that this resurfacing event corresponded to the end of the ocean and the runaway greenhouse effect. That's a big speculation. It will be exciting though. Okay, let's move to Mars. I didn't mention Mercury because it has no atmosphere. It has always been out the habitable zone, no interest. Let's start with Mars. So Mars initially was beyond the edge of the habitable zone, and now is slowly going in. And if he had a good ocean and atmosphere, it could be habitable today. In reality, when you observe Mars, you find that it's not habitable today, but it used to be habitable there at this time. There are lots of observations, and I will go super fast because it's late and it's a little parenthesis in my story. I just wanted to review the fact that we can demonstrate that Mars 3 billion years ago, 4 billion years ago, when it was young, was covered by liquid ocean with rivers and lakes. We have lots of clues for that. We have the historical one is called the valley networks. If you go to the ancient terrains with lots of craters, you find rivers, trace of rivers in many places. You can demonstrate that in the ancient terrains like here, the erosion rate that you can estimate by looking at the degradation of the big craters, smaller craters, smaller craters, you can show that the erosion rate was like that. Very high erosion, Earth-like erosion rate 3.5 billion years ago, and starting 3 billion years ago, let's say, an erosion rate which is almost negligible. See the log scale, you can see these papers here. In the 90s, we discovered everywhere in the ancient terrain layers, deposits like that. That shows like sun lines. You have lots of deposits that if you ask an earth geologist, they will tell you this is an erosion, a terrain that was eroded, but it was certainly accumulated at the bottom of an ocean or a lake. We find deltas, I won't detail. And now curiosity, all these geologists, robotic geologists are exploring places where you used to have water, sediments, very good story. And also the mineralogy where you find a lot of minerals that suggest that they were formed in the presence of liquid water. So the typical story is that Mars 3-4 billion years ago was covered by liquid water. It was habitable. Good story. But it's really a mystery. If you want to compute to understand how was that possible, you have several enigmas. So you have question that remains. Okay, we find in the geological records that there were liquid water apparently in the surface. It's not clear yet if the conditions suitable for liquid water were episodic or stable on over hundreds of millions of years. Believe me, although if you go into the literature, you can absolutely find paper that demonstrates that you had liquid water for 1 billion years, and you can find other paper demonstrating that liquid water, you only needed 1,000 years of liquid water to form everything that is observed. For some reason, there is a big debate. More and more people believe that you need several million years at least to form what is observed, or even more. For many clues that I've listed here, the minerals and some of these erosions, there is a key question is whether it was on the surface or it was subsurface hydrothermalism, notably to form all the minerals which are the product of alteration by liquid water. Many of them may be the product of hydrothermalism. And finally, we don't understand how the Mars climate could have been such that it enabled liquid water. This is in some way summarized in the plot where you see that 4 billion years ago, Mars was quite out of the likely habitable zone. And the result of that is that when we try to simulate with many details how we could have liquid water on early Mars, it's not easy. There is no simple model that does that. I won't detail that, but sometimes we speculate about the fact that maybe a lot of this precipitation is related, I don't know, for instance, by impact. It's triggered by impact. At the time, 3.8 billion years ago, you had the late heavy bombardment, lots of impacts. Maybe this is related. Maybe volcanism played a role. And nowadays, the most exciting, the most fashionable, can I say that, theory is related to hydrogen, a little bit like I mentioned before. Maybe in early Mars, you had sufficiently a large amount of hydrogen that enhanced the greenhouse effect in such a way that it went beyond, it allowed Mars to be habitable in spite of being outside the CO2 habitable zone, if you want, okay? You need something special, special role of clouds, special role of hydrogen, special role of something. And the other question that is a typical topic in Mars science is, why did Mars lose its atmosphere? Why did Mars not stay habitable? It's because it loses its atmosphere, and you have different speculation, different theories that explain that. I won't detail that too much, but a typical story is that the CO2 atmosphere in presence of liquid water formed, like on the Earth, carbonate, but there were no plate tectonic to recycle the carbonate, so there were no more atmosphere. But this is kind of dismissed now because we don't find much carbonate on the Earth, on Mars. So now the typical story is related to the escape into space. It seems a simple story, but in reality it's very difficult to escape CO2 on such a planet. But it seems that there was some process able to do that. It's now the topic of the mission MAVEN. And it seems that you can explain this, the loss of some of the atmosphere because Mars' gravity is not that high. People used to say, and you may have heard it a lot, that it's because it lost its magnetic field. And magnetic field, in some theory, prevented the erosion by the solar wind. And when the magnetic field disappeared, the atmosphere escaped. Nowadays, all the specialists don't believe that at all. They believe that the magnetic field actually do not protect and do the opposite way. It favors atmospheric escape. Yeah, it's because when you have a magnetic field, you can actually there is no simple reason for that. It's really a story. But if you have no magnetic field, if you have a magnetic field, you can actually canalize. Can I say that? Channel the solar wind, and in fact you do erosion by the solar wind indirectly. You need a photochemical reaction and so on. I can detail that. And if you have no magnetic field, in some models and in some observations of Venus, which has no magnetic field, and Mars, they find that you have a kind of shield that forms and that actually protects the atmosphere. We are working on the paper summarizing all these ideas. If you look at all these stories that did not have time to detail, it's all related to either the fact that you have a lower gravity on Mars compared to the Earth, or to the fact that you have less geophysical activity. That for the plate tectonic recycling, maybe the magnetic field and so on. So typically, the reason why Mars did not follow the destiny, the fate of the Earth is because it was too small. So, if you want to stay habitable, you need a lot of things, and particularly not to be too small. You need a sufficient gravity, maybe a magnetic field. I kept it there, but it's questioned. Maybe you need plate tectonic. Some people say that you need life initially to keep the planet habitable. It's the Gaia Theory, and there are lots of interesting stories about that. Some people mention, I just put a line there, I won't detail it, that the moon was necessary to stabilize the obliquity and then prevent too big climate change. I don't think it's necessary, but it's part of the story. I've talked about the Earth today, the solar system today, solar system evolving. Now, what about around other stars? The fact is that you have many kinds of stars, and just if I do a statistic in the solar neighborhood, you can see that you have, typically, if you take a sphere around the sun of 10 parsec, that's about 32 light years. You have about 22 star about the size of the Sun. In the jargon of astrophysics, you call that G star. The Sun is a G2 star. You have just a few bigger stars, A and F, not many. But what is really, really abundant in the galaxy and in the neighborhood are smaller stars. 90% of the stars in the galaxy are smaller than the Sun, and most of them much smaller. The K star and the M dwarf, everyone knows M dwarf if you like habitability. So, of course, it's interesting, especially to study these, especially also because these ones are very hard, these ones are cold, that's okay, but the lifetime of the big star is shorter. They evolve even more quickly. The A star habitable zone just do that, whereas the M star have a very long lifetime and the habitable zone doesn't evolve a lot. So they are interesting case. Moreover, as you may know, it's much easier to observe exoplanet around smaller star, M dwarf for instance, compared to bigger star. So this is why most studies focus on this, the exoplanet around M dwarf. So depending on the star you are around, this is a plot showing the traditional habitable zone from the masterpiece of casting in '93. This is a ratio of the mass compared to the Sun. The Sun is here with the solar system here. And you have smaller star, and here you have the habitable zone as a function of the distance. It's a log plot. And of course, if you have a smaller star, you have less energy, and you really need to be much closer to the M dwarf star, for instance, to get enough energy to stay in the habitable zone. This has some consequence. First is that if you're really close, typically if you take a very small M dwarf, you need to be a few astronomical units away. It's really close. You're not far from the activity of the star. You can get some, how do you call that, flares affecting your planet. You really have a very strong solar wind that can affect you, especially when the star is young. I told you that the star tends to be stable, but the star stays young much longer than a bigger star. M dwarf star can stay young for 100 million years. When I say young, if for 100 million years, its flux will be higher than what it will be when it will be on the main sequence, just like what the Sun was when it was really young, but the Sun was really active, telluric type and so on for only a few million years, or even less, whereas M dwarf star can stay very active and young, I will say, for 10 or 100 million years. So it's enough for that time for the planet to have a runaway greenhouse effect and so on. So let's go back to this story about the habitable zone and so on around K and M dwarf star. What happens when you are around the M dwarf star, for instance, you have a redder stellar spectrum. And that changed a little bit the story I gave you before. For instance, you have a weak atmospheric ray scattering, you have a lower planetary albedo, so that you need, you will go into runaway greenhouse effect even for a lower flux. That's okay, it just changed the shape of you can see here, the shape of the habitable zone. More interestingly, you have the effect of tides. Just like the moon around the Earth, when you're in the habitable zone around a small star, you tend to show the same face to the star, and typically every planet will at least have a resonant rotation with a zero obliquity. So you will have the pole which will be cold and the equator quite warm. And in many cases, you have a locking with a permanent night side and a permanent day side. What's interesting for this problem of the runaway greenhouse effect is that when you model the climate in such a case, when you are tidally locked with a permanent day side and permanent night side slowly rotating due to the tides, you find that you tend to have clouds forming only on the day side. You have a very high albedo on the day side because of all these clouds, whereas the night side remains cold. And if you do the math or you do the simulation, you find that this is very efficient to protect the planet from going into runaway greenhouse effect. So this was found by Jeremy Lecomte some time ago with our model, but actually published first by Jun Yang at the University of Chicago, and you can see the title here summarizing this idea. Stabilizing cloud feedback dramatically expands the habitable zone of tidally locked planets, because again, you have this shield of clouds forming only on one side, and on the night side you can cool the planet. And the albedo effect is really asymmetric, and this time it works, whereas, if you remember, I told you that when you do that on an Earth-like planet around a Sun-like star, the clouds tend to actually enhance the greenhouse effect. A word about the glaciation. It's a little bit different. Again, you have a redo stellar spectrum, and you can show that if you have if you are around a star which is red enough, small enough, then suddenly water ice and snow is not the bright material that we know on the Earth. If you were on such a red planet, you have lots of flux coming in the near infrared, and in the near infrared, this is a typical spectra. Let's look at this green stuff. This is snow albedo. The snow is really bright at the visible wavelength, but starting at 1 micron, it drops, and actually snow is super dark in the near infrared. Since around such a star, most of the flux is not like the sun here, but like this, well, suddenly the snow is no more something bright and reflecting radiation. It's something which is actually dark and absorbing radiation. So you have no more no albedo water ice feedback, or at least it is reduced. Doesn't change much the story, but in some details, yes. I will go fast on this because it's late. Just to say that it changed a little bit the story for the greenhouse effect of CO2. And again, you have the effect of tidal rotation, and we can wonder if it will be a problem, because if you are cold and you have a super cold pole because you have no obliquity, maybe all the ice and CO2 and gas will be frozen there. And even worse, if you have a permanent, if you are completely locked with a permanent night side, maybe all the atmosphere, all the water can be stored there, and you have no liquid water available on the day side. So this is a summary of this is a more recent plot showing the habitable zone as it is discussed today in the literature. This is adapted from Sarah Seeger, and you can see the kind of plot we do today. This is the mass of the star relative to the sun. The sun is here, smaller star. These are the stars that have been observed, and this is the distance. And you can see that you have, as I mentioned at the beginning, you have different kind of habitable zone, because you can take the one for Earth-like planets, the one for dry terrestrial planet or slow rotating planet, if you take into account hydrogen atmosphere planet, as I discussed before. So I will finish with a few stories. First question, have we already detected potentially surface habitable planets? And I will use this to give you a few examples of investigation we've done on possible climate on other stars. In the year 2000s, the only thing we could detect were giant planets. But we discovered right away a lot of giant planets in the habitable zone of various stars. So it was already exciting. At the time, if you look at the science fiction literature and movies, it's all about giant planet in the habitable zone and with habitable moons. You can see a lot of this because all the planets we could say. So for instance, at the time you had this famous movie, Avatar, and Avatar is a habitable moon around, I think, Alpha Centauri, Alpha Centauris, because it's a moon around the giant planet. We could detect the giant planet, not the moon. Then, in the mid-2000s, we started to detect not Earth-sized planet, but super-Earth. And one of the big discovery at the time was the system of Gliese 581, discovered with ARPS. And it was very exciting because quite quickly it was discovered that it was a system with several planets. And this planet, at least the C, the D, had a mass which was which was consistent with them being super Earth, in other words, terrestrial planets, rocky planets. So at the time, everyone was excited. The publication by Stéphane Udry in 2007 The first publication was, okay, that's the Habitability search for southern exoplanet. They have published 40 papers like that. But number 11 was an habitable super Earth in a 3-planet system. This was super exciting. This was the very first terrestrial planet discovered in the habitable zone of any star. So this made headlines. This is in French, sorry, but it was very exciting. But then it was put on archive. Everyone knows archive. And Frank Celsis in Bordeaux next door said, what are you talking about? Gliese 581c is there, so it receives more energy than Venus. It cannot be habitable. The astronomer says, oh no, we estimated the brightness temperature and it's 40K, it's okay. No, 40 Celsius. It's not okay because if you put an ocean, right away it goes into run a greenhouse effect. So they got convinced, and this is the preprint, but the final article is like that. Super Earth in a 3-solar system. Okay. Then, in 2010, the US team, using their own data and some of the data from HARPS, decided that they have discovered a 3.1 mass planet, Earth mass planet, in the around Gliese 581, a new one, 581G. And this one was super exciting. Okay, this is a plot showing the habitable zone of Gliese 581, and this is where it was, in the middle habitable zone. Everyone was excited, starting with the first author, Stephen Vogt, who gave interview saying that he was absolutely convinced that the planet was habitable. Even named it after his wife. In the acknowledgement, you can say it says that this planet that he had discovered should always be known as Zarmina's world. Zarmina's Vogt is Stephen Vogt's wife. That was cool, and it made headlines as well. Gliese 581G, the world of Zarmina. But quite quickly, the HARPS team and some statisticians demonstrated that this planet did not exist. It was an artifact.
Nice result.
Then, with Robin Wentworth working in our team at the time, we say, hey, about Planet D. Initially, Planet D was a little not considered too much because it is really cold in theory. Its equilibrium temperature is minus 80 Celsius. And it is most very likely locked in synchronous rotation. So that it is cold, no insolation at the pole, and probably a permanent night side. So everything was so cold that people were skeptical about the idea that this could be habitable. So with Robin, we did some calculation using the kind of model I told you about to explore what will be the climate with the CO2, nitrogen, H2O atmosphere. This is Robin. So these calculations are quite fun to follow. You have CO2 ice clouds forming, having greenhouse effect. You have water clouds. You have lots of action going on. To go quick, we could easily demonstrate that it will be very easily habitable. One of the reasons being that even if you neglect the ocean, in such a planet slowly rotating, you have a dynamical process called superrotation that efficiently transports the heat from the day side to the night side, so that it's not easy to freeze everything on the night side. And ultimately, I won't detail that, but we could find, depending on the assumption of the rotation rate and so on, if you assume a little bit of CO2 and nitrogen, it was easy to have a habitable planet with lots of liquid water. So we were super proud. We published this paper entitled Gliese 581 is the first discovered terrestrial mass exoplanet in the habitable zone. We were very proud. We made a lot of news coverage with that in Europe and in the US, but not in France, because we announced that the exact same day that Dominique Strauss-Kahn was arrested, so there were no more other news in France for the French people here. Anyway, so we are proud, much, I mean, really with lots of content to Stephen Vogt, who has announced his wrong planet, but we were wrong. Because years later, that's 2014, it was announced that stellar activity masquerading as planets in the habitable zone of the M dwarf Gliese 581. That means there is no planet D. Well, there were a debate. Some teams say, no, you're wrong, and they say, no, we're right. I don't know. I think it... To be honest, I think it does not exist. I think the first paper is quite convincing. There is no planet D. I just wanted to illustrate you the kind of debates we have. There have been, since then, this is 10 years ago in some way, there have been a lot of discovery of planets which are clearly terrestrial in the habitable zone of their star. For instance, if you take the Kepler catalog, you have lots of examples. Some are can be discussed, of course. Kepler 552b is a little too warm in my opinion, but many of these works very well. So there is no first to announce about planet that could be habitable. We have no idea if there is water or an atmosphere around these, but they are at least in the habitable zone. We got an exciting announcement in 2016 with the discovery of Proxima b. It's an Earth-sized planet and which was found around the star closest to the Sun. It's one of the best, smaller, best located planets that we found, and it was around the star closest to the Sun. That was a very good story. So I won't detail that, but Proxima is a small M star, 12% the mass of the Sun, so it's really red. It's an ultra cool dwarf. But Proxima b is well located. It's a little bit inside the habitable zone compared to the Earth. I mean, outside, colder, little colder in terms of flux, but it works very well. And it was very interesting to explore the environment of Proxima b. So there have been several papers on that. I wanted to mention the work by Martin Turbet. And again, to illustrate to you the kind of challenge we have to address when we want to explore the possible climate, the habitability of such a planet. So you can take GCM, I told you, you just say, okay, we have an ocean, no ocean. You can say this more or less CO2, more or less nitrogen, more or less whatever you want, and you say what will happen. When you want to do that seriously, you face a new challenge compared to the list of 4 models that I told you. Typically, when you take a full global climate model, you have to assume oceans, or you have to say ice is there and something like that. But you cannot do that. To have a really good modeling of the climate, not only you have to simulate the climate for years, but you have to simulate the climate for hundreds of thousands of years so that you can understand where, if you put water on this system, the water will go. Will it freeze on the night side? Will it make glacier on the pole, which will cover the planet? So that's the kind of work that has been done. When you have a limited water inventory, you need a full 3D GCN with what we call the converged water cycle to simulate where the water reservoirs are. Because they don't go when it's warm and it can melt. They go when it's cold. You have cold trapping. If you have a lot of water, it seems to be easier, but no. Because then if you have a lot of water, then you have a global ocean, and then you have to take into account to fully simulate the climate impact of the ocean on using a 3-dimensional ocean model, and that's another complexity. So there is a level 5 in this complexity with these problems. Very quickly, Martin Turbet did a lot of simulations and could summarize his finding with such a plot. Such a plot shows you typically for assuming, for instance, synchronous rotation. It takes all what we know about Proxima b, and it takes a planet, put various amount of gas, nitrogen, CO2, and various amount of water, and then let it go for a long time and check what happened. And this is what he finds. Typically, when you start with not much water, you have no water, but if you have a little bit, depending on the CO2 you have, if you have too much CO2, you're too warm, all water is in vapor state. If you're too cold, then everything will be dry and all water will be stored as glacier on the night side. Then if you have more water in the system, then the water tends to accumulate on the night side, okay, but it will flow to the day side. Either you have lots of glacier flowing or you have liquid water flowing, and depending on the greenhouse effect you have this different possible regime. For instance, here, this is a regime where you have a lot of water but a cold temperature, so you have a glacier there and some water flowing to the day side, and here will be super dry. If you have a lot of water, then you have a complete ocean. If you don't have a very strong greenhouse effect, everything will be frozen except the substellar point where you have open ocean. This is called the eyeball solution, which was published before by Pierre and Pierre. It works very well. If you have lots of water vapor, whatever you have for greenhouse effect, you have liquid water somewhere. If you have more CO2 in the system, more greenhouse effect, then you can have less ice and more liquid water. And if you have a lot of CO2, then everything is unfrozen with, as you can see, this little point where you have water ice clouds near the substellar point as I described before. What is interesting in this story is that if, for Proxima b, you assume you have a high inventory of water, more than on the Earth typically, well, then whatever you do, you have liquid water somewhere. It has to be habitable. It's interesting because it is quite likely that Proxima b is volatile rich and certainly water rich. Then the debate is whether if it started, for instance, with, I don't know, 5 Earth ocean in quantity, whether it survived the initial period during which the star, as I mentioned, was very active, typically 100 million years. Maybe 4 oceans escaped and 1 ocean was left, so that you were in this regime. A question that can be asked is why is this interesting if Proxima b is closed? Compared to all the planets, very interesting planet that has been discovered by ARPS or by Kepler. The answer is not because we can go there. It's not possible to go there. Even though it's the closest star, as you know, it will take 70,000 years for Voyager 1, the fastest spacecraft currently, to go there. There have been speculation about faster spacecraft, but I won't detail them. No, it's cool because we can observe it. So I have no time to detail that, but the story is that currently it's difficult to do much about it, but with the extremely large telescope that should be ready around 2025, maybe later, we will be able to do direct imaging, distinguish Proxima b from its star, and do spectroscopy, and be able to characterize its atmosphere. And if we're super good, characterize if it has an ocean or not. But this is not the ideal case. The ideal case when you want to observe an atmosphere and see if a planet is habitable is to have the case where you are lucky to see the system by the edge so that you have the planet transiting in front of the star. So it was disappointing to find that Proxima b is not like that. It is now demonstrated it's not transiting. So we don't have easy progression. But the big exciting observations that has been performed since was this suite of observations. It's the Trappist One system. Everyone knew about Trappist One? Trappist One is a 7 Earth-size or smaller planet that has been observed around a very small star. And I will go very fast. It is super exciting because we will be able to observe most of this planet by transit. And it has now become the priority for future observation, notably with the James Webb Space Telescope. About habitability, we can show that Trappist E is like Proxima b. If there is enough water in the system, it will be habitable. We can almost demonstrate it. F and G are a little further away from the star. They need greenhouse gas to be habitable. These ones here are too warm, and if you do the climate calculation, they tend to all be in runaway greenhouse state. So this will be the objective of James Webb. So the problem with James Webb is that every year the launch is postponed by 2 years. So we hope it will be launched soon. And even though it was not at all developed when Trappist system was known, now a lot of the time that is allocated for the various instrument leader and the telescope leader will be allocated to observe the Trappist system. Okay, I'm almost done. This is a first conclusion. I told you that to know about the habitability and climate, we need to know these 3 parameters. I told you that we can model that well, and it did. For a given parameter and atmosphere, I think models as I described them, can do a good work to explore the possible climate and the possible habitability. Of course, you need to do a lot of model sensitivity studies to be confident in what you find, but if you assume this, you can find this. Of course, the big problem is that to estimate if there is a lot of planet habitable or not, is that we don't know much about the possible composition of the atmosphere. It's very difficult to understand the zoo, the possible zoo that we have for atmospheric composition. It's controlled by complex processes. The formation of the planet of the atmosphere, the escape to space, is controlled by the interaction with the subsurface and the outgassing and stuff like that, the photochemical evolution. And these are much more complex to model than climate, in my opinion. Of course, my job is to model climate, but I think it's difficult. Also, our experience in the solar system is not sufficient. If we didn't have Venus in the solar system, I'm not sure we could dare imagining a planet with 90 bars of CO2 and so on. If we didn't have Titan, we just will not imagine Titan. So it is very likely that around other planets there are plenty of very weird planets, very weird atmosphere, and it's difficult to imagine them. Just advertise the fact that in some papers we've been trying to brainstorm about the kind of atmosphere we can have. And we felt really a little stupid in the fact that the only thing we could think of are in some way related to experience in the solar system. And whenever we want to be exotic, there is always a good reason, probably wrong, that suggests that it cannot happen. What I mean is that this is a plot where we show the kind of atmosphere we can expect as a function of the mass and the distance from the star, typically. In such a plot, for instance, the Earth is there, where you have mostly CO2, some nitrogen. Mars is there, and I could continue. I won't have time to detail these different cases. Some are exotic, okay? For instance, if you imagine a Venus-like planet, but a little more massive, instead of losing water completely directly, you could lose hydrogen, but oxygen will stay and could have a thick oxygen atmosphere. If you have a super thick planet with a lot of water in the system, which is going into runaway, you will have an entire atmosphere made of H2. It's called a steam atmosphere planet. Why not? But still, it's all related to experience. And we need observations to fill the zoo and have more exotic stuff in the system. But right now, as for me, I'm not able to imagine very exotic case. So this is the conclusion. I won't repeat that. I repeat some words about habitability, the definition about the habitable zone. But my conclusion point, again, is the key open question is what does it take for a planet in the habitable zone to be and remain habitable? And especially, what kind of atmosphere does it take? On the Earth and in the solar system, our understanding is biased. It's a kind of entropic principle. You know, the entropic principle is the fact that we have learned geophysics and astronomy from a planet that works. This planet might be completely exceptional. It is possible. Because it's not by coincidence that we are on it. We are in a system on a planet that perfectly works to have an ocean for billions of years without interruption for life to develop. Maybe it's exceptional, maybe it's not. So what is interesting is that we will make progress in that investigation in the future, because soon we'll get observation of atmosphere from the James Webb Space Telescope, the European and other extremely large telescope. Ariel, I did not mention it, it's a space telescope designed to monitor many kinds of atmosphere, mostly about big planets, but it will be super interesting. So we will learn a lot from atmosphere, even outside the habitable zone. It's okay if I fill my zoo with stuff which is too cold or too warm. At least we'll make progress in this question. What kind of atmosphere can we expect, and what kind of volatile inventory can we expect elsewhere? Thank you. I will finish here.